Huh. So let's explore blockchain today. Uh, I'm trying to look into some blockchain papers, and I have a book. This is Mastering Bitcoin, I guess, by O'Reilly. So I wanted to read some blockchain papers if they are of any use. I don't know, like, what's the quality of papers in this domain. I mean, it's a relatively new field, so I think, yeah, first I have to read this. The original Bitcoin paper, what's that called? I think I have that. Yeah. Hmm. Let's just take this out. I guess this is the first paper, like, on Bitcoin, and it was written by someone called Satoshi Nakamoto. It's anonymous, I guess. It's, yeah, he is anonymous. So I wanted to know, like, so this is like what's happening. Right, so Bitcoin runs on blockchain tech. Right, so in order to understand Bitcoin completely, you have to know blockchain. So what I know is that blockchain is a peer-to-peer network where we store, where every transaction is stored and is immutable, which means we can't change that. So once a transaction or once a block, yeah, it's transaction, it's into the network, then it is impossible to immute or change it, because so there are blocks, right? So each, let's say there's B1 and it has a child B2, this has a child B3, right? So each one has hash, I mean, it's unique hash. So B2, B3, right? B3's hash is derived from B2 and B2's hash is derived from B1. So if you want to change, let's say, B3's hash, or if you want to change any data in the B3 block, uh, which happens to change the hash as well, because hash is something that's calculated by the data inside the block. So if you have to change something inside block 3, then this has to change block 2's hash, because um, this B3's hash was calculated based upon its parent block, right? So again, similarly, that chain continues, and B2's hash has to be changed, then B1's has to be changed. So this in a large network is not recommended, and it's very slow. So that's the reason blocks are immutable, transactions are immutable. So let's see if there is any open books, open library. So what's this book name? So I think it's by O'Reilly. Yeah, this one. How do I download this? I guess I have downloaded this online actually. Is it the same? Let's search here. Wow. Okay. So yeah, there is this blockchain chapter, right? So I want to go there. So how do I go to 159? Yeah. No. So there is this block, right? Right. So this aggregates transactions to include in the ledger. What's the ledger? A usual ledger means a list of records, I guess. Yeah, it's a collection of financial accounts. So average block contains more than 500 transactions. So I think there's another important concept is the block header, because I've heard that many times. So it contains the metadata, right, of the block. So this is about 80 bytes. So is it strictly 80 bytes? Yeah, I guess so. So I have also seen that there is this proof of work algorithm, right? Let's get to this afterwards. I guess this comes under mining, I guess, because you have to you have to mine or solve that problem, in which varies of difficulties, in order to mine a Bitcoin, right? Yeah, it's in mining. Yeah, block header is metadata. So in block header we have version, previous block. Yeah, this is what I was saying. So we have this previous block hash, right? So the parent block chain, block in the chain. So block header contains the previous block hash which we were talking about. So previous in the sense it's the parent. Yeah, this was also another thing we were talking about, difficulty target. So the proof of work algorithm difficulty target for this block, and nonce is the counter. So what does that mean? And how is difficulty target used in block header? Block header hash and block identifier. Yeah, so this is also quite vital for a blockchain or a block, because to identify a block, so we have its we identify by its cryptographic hash. Okay, by hashing the block header twice, right? We obtain this hash by hashing the block header itself. Wow. Okay, that too twice, using the okay, let's go using SHA-256 algorithm. I think this is the same algorithm used in Git as well. I mean, they have moved on from SHA-256, but yeah. So there is also some tricky questions, like if there is a collision on Git when they're using this hash, then there will be many inconsistencies. Like we could see other codes, like even if it's a private repo, we could see their code on our system if their hashes collide with ours. I don't know how true is that. I think there's a notice from them. I don't know. Let's see. To a stronger hash function. So what's the hash they're using? Okay, they picked up 256 SHA 256 after SHA1, ditching SHA1, right? So aren't they moving away from 256 again? Okay, they are using 256 by moving from SHA1, or is it? Okay. Okay, so we are hashing this block header twice using this SHA 256 SHA-256 algorithm, and we hash the block header and we get the hash of that block used to uniquely identify that block. So that's the first way. You identify it using its by its cryptographic hash. Second way is to identify a block by its position in the blockchain, called the blockade. Yeah, so I have heard about this. Like each time a block is added, the block height is incremented, right? So let's say there are in the blockchain or network there are like 15 blocks, then that 15 number is called the block height. So let's say the some block we want let's say some block with hash ABC, and it's at the position number 10 in the network, then its block height is said to be 10. So it's like a stack, so each block is appended to that stack. So how, okay, you if you have the block height, then you can find the block. Yeah, using by its block height, each block is appended on top of the topmost block in the network. Yeah, so the block height is not a unique identifier. Why? So this is unique. So 2 isn't unique exactly, because there can be two blocks fighting for that block height, called as block fork. What's that? Blockchain forks. So this Genesis block, so this is the first block, right? First block in the blockchain. Okay, every node always knows the Genesis blocks hash. So what's the difference between node and a block? I'm confused. Okay, so node is so basically node is a pair, right? So because it's a P2P network, a node is a pair. More nodes equals to more decentralization. So linking blocks. Yeah, it's basically so block has has this previous block header hash, right? So it has this previous block header hash, and when a node sees this in a block, it links it. Let's yeah, it links it. Therefore, links it. That thus extending the blockchain. Merkle trees. I have heard about this. I know this is. I think there's Merkle trees. Is it a trie in data structure? Yeah, it's a combination of Patricia trie, Radix trie. Okay. Okay, so a Merkle tree is a tree which summarizes all the transactions in a block, right? Yeah, so what's the use case? That's the first question that came to my mind. To let's say visualize or to store. Is it to store? Or let's summarize all transactions in a block. So this is a efficient way to do summarize um, because of the complexity that it takes to get an element in the tree, which is to login, right? Basically login. So what does it actually do? Okay, it's a bottom-up approach. Yeah. So we start with 4 transactions A, B, C and D, which form the leaves of the Merkle tree. The transactions are not stored in the Merkle tree, rather the data is hashed and the resulting hash is stored in each leaf node HA, HB, HC, HD. Yeah, so I mean it makes sense because you do not store all the data, right? You can just hash it. And how do you determine the leaves of a Merkle tree? So they say that 4 transactions which form the leaves of the Merkle tree. Okay, these okay, so I guess so we were discussing like each block is derived from the hash of its parent block, right? So we can use that property in order to construct a tree. Each block's hash is derived from its parents, but no, it is a transaction, right? I guess this applies same for the transaction too. um, okay, so these are not the transactions, so every transaction is a leaf node, right? Then what's this? So every transaction is a leaf node. So they are saying there are 4 transactions and the 4 of them will be a leaf node, and the reason we are hashing it is to get from the root to the destination transaction. It is easier than going, if you want to go to D, you don't need to go A B C D. You can just do it in let's say A B C D, then you go to C D, then you go to D. So it's just 2 steps instead of 4 steps. That's what they were saying about the login approach. So each transaction is a leaf node, leaf node, and intermediate hashes are calculated into nodes or calculated. Makes it easier to reach the destination transaction. So it also says it duplicates a transaction if the tree is not balanced. So here, if there is only ABC, then this C, it's duplicated here. Several hundred to thousand, more than 1,000 transactions in a single block, which are summarized in exactly the same way. So thousands of transactions can be stored in just 32 bytes of data. That's cool. Can be stored in the sense like we don't require the entire data. We just need the transaction ID or the destination transaction. So this page is just telling us how it's helpful. Like we can know, let's say this HK exists, a HK transaction exists, by just if we know that, let's say this 1, 2, 3 and 4 transaction hashes, using that we know that we can know that the HK hash exists. Even at 16 MB, which is 65,535 transactions, the size stands at 512 bytes. Can be stored under 512. So SPV, which is Fied Payment Verification, uses Merkle tree to verify if a transaction exists in a block. Nice. So that was blockchain. So this is mining. So what all were there? So this actually expires at 2:59. So there's 30 minutes more. So what if we go to the first? Transactions. I think we can go into transactions a bit. Even the Bitcoin network seems interesting. Yeah, let's go to transactions. Am I audible? I can see that it's dropped. I don't know what's wrong. Check. There you go. So the life cycle, let's say, transaction, let's say TXN is signed by one or more signatures. So then after signing, then the transaction is populated or broadcasted, as they say, into the network. So I think the work of miners is to verify the transaction, I guess, isn't it? Transaction is broadcast into the network, and then each network node, so each node validates this transaction and propagates to other nodes, I guess. Yeah. So finally, transaction is verified by a mining node and included in a block of transactions in the blockchain. So they're comparing this transaction with credit card transactions. So credit card transactions, I think they are very carefully written and they're carefully handled because it contains sensitive information when they're transmitting information from one device to another. But in the case of Bitcoin network, because it's peer-to-peer, the transaction first of all doesn't contain any sensitive information. So first it's, and more than that, it's just a data structure, as I say, right? It's just, I mean, you can boil it down to bits and bytes, but more than that, it's just some ASCII characters, right? Which is not sensitive. So you can just send it however you want. You can even send it as satellite relay. Nice. So since this network is a peer-to-peer network, as I say, so each node or a peer is connected to some few other pairs and they are connected to some other, and like this it forms the network, right? So that's the reason, like if there are many pairs, then more decentralized it is. Like you can have many pairs, which means the verification of the transaction can be done by all the pairs. If there are high number of pairs, then it's that strong or it's that secure. Yeah, the structure of transaction. The version input counter, inputs, output counter, outputs, lock time. What's lock time? I mean, they say it's a lock time, but the description it's a block number. Why is it? So this is a timestamp when the transaction is verified, and okay. So we have version, we have input counter, input, output counter, output, and we have lock time. So this is the earliest time when the transaction was valid. So this is a single transaction, and what's an input in a transaction? Okay, I think what's happening is, so the input is credit, output is debit. So credit in the sense money coming in, debit in the sense money going out. So usually what's happening in a blockchain or a Bitcoin basically is when you spend, or when, let's say, when a transaction is done where money is sent from one address to another. So let's say the balance is $10. Then if you want to spend or if you want to transfer send, let's say, $4 to from this address, let's say ABCD to FGHIJ, right? So what happens is we can't send just the $4, and I mean you can't subtract 4 from 10 and then send $60 from ABCDE to this FGHIJ. So what happens is you first send the $10 to FGHIJ, right? So that's one transaction. So send $10 from ABCDE to FGHIJ, and then what happens is receive let's say 10 minus $4 is equal to $6 from FGHIJ to ABCDE. Right, so the reason this is, so even if you take in the real world example, if you want to, let's say the shopkeeper is asking for $60, you can't give exact $60 because there is no $60 note, right? So you give maybe 50 plus 10 or 6 $10 notes, or let's say you give even $100 note and ask $40 in return. It's the same way this happens. When you look into the history of the transactions, I mean usually what it shows is we have sent $4, but inside the block, if you see the transactions, you will have this received $6 also. So that's another transaction. So if you want to send amount from one address to another, there are two transactions happening. Okay, here it is. I mean, lock time is here. UTXO means unspent transaction outputs. Yeah, this is just what we were talking about. I think it's the same thing. Let's return the book and then borrow it again. Oh, I can't borrow it again. Shit. page number 109 or 119, I guess. Okay, this is an early release. Okay, let's just go with this. Viewer. Yep. So you don't want to go too much deep into all the topics. I'm just seeing what are the major topics, like what are the important topics that I can get from blockchain to get a basic understanding. I think we can skip transactions for now. Yeah, we can skip it. We can go to Bitcoin network, or we could do keys, addresses, and wallets. Not everything, but I think we can go to Bitcoin network. So this is nodes usually run the Bitcoin code, right, or the client. I think it's on GitHub. Yeah, so you can install this. I mean, you can clone this repo, and what it does is it starts getting information of all the blocks in the blockchain. So that's really heavy, I guess. I mean, if we are using a general computer, there's no need to clone even this repo. You can just look at it. So it's basically to discover the network, like when a node starts up and then it want to know what other nodes are there, and it's also saying it's not geographically defined, which means location doesn't matter. So upon starting, nodes start a TCP connection on some port. Here it's 8333, and then where does it? So it starts with the handshake. It's basic TCP protocol, I guess. Yeah. So this is three-way handshake. Or it's two-way. Okay. So in this there is, let's go a bit lower. There's seed node, which is a stable seed nodes, let's say stable nodes which long run stable nodes, right? So if a new node connects to one of the seed node, if a new node connects to a seed node, it's easier to get other nodes, other blocks, no nodes. So it's basically finding pairs, because a new node sends its own IP address to other nodes, and they to others, and so on. So this way the new node is known by all other nodes, making and if it wants to verify a transaction, let's say, then this new node is known to all other nodes, so those transactions will also be sent to this node to verify, I guess, if I'm not wrong. Yeah, I think basically you need peers for that only, right? Okay, you can get peer info. Actually, let's deep dive into the Bitcoin CLI sometime. So there's a list of peers. Okay, there is something called full nodes. So these are the nodes which, or you can say nodes or computers or pairs which have a complete um, copies, or you can say a complete blockchain with all transactions and all blocks, right? So it, as it states in this, it takes over 20 GB and 2 to 3 days to sync. So why do we need this? Okay, why does a node need to be a full node? So the reason is that so usually if it's not a full node, so if it doesn't have the complete information, then the node has to depend on other systems to, let's say, to verify a transaction or to talk or whatever it needs, because it doesn't have the information, so it relies on other nodes. So that's what basically P2P system is, right? So node usually relies on other pairs in order to do something or do stuff, because that node doesn't have enough information, enough data. A full node does have all the data. All the data in the sense every block, every transaction it has. So it doesn't need any other pair, right? So it's independent of any other node in the blockchain. So that's what a full node is. Let's try this someday. I really want to try the Bitcoin. Let's clone this and I want to try this actually. So when we, let's say, clone this repo and we are the new node, then it needs to start with some block. So there is this genesis block which is into every node so that it can start from there. That's like the initial block. So Bloom filters, I know this is a data structure to see if an entry exists in a set of entries or not. So I even have a YouTube video on it explaining how this data structure works. Why do they use this in Bitcoin or blockchain? So SPV nodes, why? SPV nodes use Bloom filters to ask their peers for transactions matching a specific pattern. Bloom filters does this by protecting their privacy as well. Yeah, this basic Bloom filter implementation. Okay, I guess that's for the Bitcoin chapter. So I think mining is something we need to see. Hmm. So list of transactions in that block, confirmations. We need to see what are confirmations, and we have in the Merkle root, so which can be used to find a transaction, I guess. So what are confirmations in a block? Okay, so confirmation is the number of nodes who have confirmed that this block is valid, I guess. Yeah. Hmm. Yeah, this is a difficulty which I guess we could. I will actually read more about this, and after that, I can stream on diving into the code base of Bitcoin, and then we can run some commands and see if it's working or not. That would be interesting. Yeah. So I guess this mining is pending. I'll just read on this, but I have a basic idea of how this works. Yeah. So yeah, the next stream would be to uh, dive or to see what the Bitcoin commands are. And the following streams, I guess we could do something like using code. We can do something like transactions via code and sending money. That would be really interesting from scratch. Or yeah, that would be really, really interesting. Yeah. Okay. See you. I'm just ending the stream. Bye.